So in this video, we will try to find an expression for a mathematical expression for an inductance of a solenoid, and we'll try to generalize some kind of a mathematical definition of inductance. Maybe let's put here what we have so far done. So inductance is the opposition to changing current. So opposition to changing current, changing I. And so let's start with the flux, the magnetic flux, and we'll try to build to it. Oh well, let me add something to it, and then good inductor is a solenoid, and then versions of a solenoid would be a toroid, where you take the solenoid and you bend the solenoid into a circle. You can increase the inductance of a solenoid if you insert an ion core into it. But anyways, so let's start with the magnetic flux. And magnetic flux is defined as, well, this is the proper definition, where it's B dot dA. For those of you who did not take calculus class, but the algebra-based class, the inductance is B that A, or just B times A times the cosine of the angle theta. And then note that all of the expressions we had for the magnetic field were in the following form. It was the magnetic field equals some kind of a constant times I. If it was the magnetic field set up by a straight wire, it was current I times a specific constant. If it was the magnetic field set up by a loop, it was current I times a different constant. If it was the magnetic field set up by a solenoid, it was current I times yet a different constant, but it was always really just I, current I times some constant. And so we can say that the magnetic field is proportional to the current I, right? So if I is increasing, so is magnetic field, and it's just a proportionality of it. They're just proportional to each other. You put a constant in front of I and you have equality. So you could then do the following, and this perhaps is a little tricky to see, but you could take this and you can rewrite magnetic flux as, well, if the magnetic field is proportional to I, then so is the flux. And so you could write that magnetic flux is going to be some constant times the current I, and that's fine. You can do that. If I is proportional, if the magnetic field is proportional to the current I, and pretty clear that the flux is proportional to the magnetic field, then you're justified in writing this. So L would be some kind of a constant of proportionality. So for the moment, I'm just going to write that L is a constant of proportionality. All right, and then what we want to do now is maybe add something to it, so that what I'm going to write is, I'll go this route here. I'm going to take the derivative of both sides, so that I have d phi dt equals L is a constant, so then I just have di dt. And that is kind of the same as, so I'll take the algebra route here. You could rewrite this as the change of the flux with respect to time equals L times the change of the current with respect to time, so I over T. And remember that this here, and similarly this here, is just going to be the EMF. So what I get here is, by Faraday's law, this is just minus EMF equals L times I over time. Here this is EMF equals L times di dt. And in case you forgot, we define EMF as minus change of the flux over time, and of course this can take the derivative everywhere you see deltas. And so now we are moving somewhere, because I'll take another step and I'm going to replace this EMF with voltage. because I think it's a little easier to see where this is going this way. So then this would be minus L times di dt, and I'll rewrite this here. This is L times, so there's the I'm going to bring minus the, oh, I wanted the voltage. So this is voltage equals minus L times I over time, and then recall that voltage, that actually will do. Now I think we are ready to sort of see what this L is. Here's the circuit. You've just closed the switch, right? And the current flows through this thing. So you have the current that flows, I, and this thing I is increasing. And as I is increasing, the magnetic field, due to this current that points into the page, this B is also increasing. And then by Lenz's law, you're going to end up with an opposing magnetic field that points out of the page. So there's B opposing, and then this magnetic field that opposes, the blue field, is going to be produced by a current that flows in the opposite direction, so it flows like this. But of course, if you are to have a current that flows anywhere, then you must have some kind of a voltage. So there's an opposing current, so I'm going to put here I opposing. And this comes from some kind of a opposing voltage, so delta V opposing. And so you can look at this equation. Which one should we? Let's do this one. If we look at this equation here, you can think of this as the opposing V, opposing voltage. Yeah, let's just have that. So this is the V that opposes, and it is due to the increasing current I. So here's I that increases, I that increases, increasing I. So we have increasing I, current I that is increasing, then you have delta V that opposes the increase, and you can calculate both of them. However, note that there is a constant of proportionality in between the two. That is, the bigger the change of the current, the bigger the opposing voltage, right? This is just proportionality between them. So the bigger the change in current in a loop, the bigger the opposing voltage. But there's this L between the two. And the bigger this L, the bigger the opposing voltage. And the bigger the opposing voltage, the bigger the current that you have in opposite direction eventually. So you have the bigger this constant L, the bigger the opposing voltage. And so it would make sense to pin this L to the concept of inductance. And so we're going to say that, well, first of all, maybe what I'll write is the bigger L, the bigger opposing voltage. And so it makes sense to tie this L with the concept of inductance. All right, so I have motivated some sort of a mathematical formulation for the inductance here. And generally speaking, the definition of inductance is just sort of this expression here where you have EMF equals minus L times di dt. That will do for the general definition. And now what we'll do is we'll try to use this to find an expression for the inductance of an inductor. And so let's move this up. Oh, can't do that. Let's move it to the left. And so let's add, that should be enough room for us. So inductance of an inductor. Well, of a solenoid, really what I want to do, solenoid. Otherwise, I'm just saying, anyways, of a solenoid. And so what I'm looking for is, well, let's do it like this. So we sort of said that the flux can be defined as L times I. And then for the case of an inductor, if I have a current that flows into this and then flows out of this, then I will have a magnetic field that is set up here inside of this solenoid, and that equation for that magnetic field is mu naught times I times number of loops over the length. I'm going to use little l here. You'll see why I want to use little l. The little l, so the little l is the length of this solenoid, so that's going to be little l here. The flux is the flux of the magnetic field through the solenoid is just going to be the magnetic field B times the area of a single loop times the number of loops, right? This here is the flux through a single loop, and then if I want the flux through the whole solenoid, I take the flux through the single loop multiplied by the number of loops I have. And so now I'm going to combine these two equations here to end up with L times I equals B times A times N. And let's take it a little farther. For the magnetic field, I'll have mu naught times I times N over L times A times N. And then the current cancels. Now I have my expression for L, the inductance of the solenoid, which is mu naught times N squared over, that's little l, over little l times A. And that is really, for the purposes of our class, this is the only equation I think you will need, unless we do toroid, but I think we only do the solenoid. This is the only equation you will need, the equation for the inductance of a solenoid. So I'm going to put here inductance of a solenoid. Now units for inductance are henries. Henry or just H. All right, so to maybe briefly summarize this, inductance is the opposition to a changing current. And then we have, so this is sort of one point. Second point is that the inductance L of the solenoid is what we have up there. So mu naught times N squared over the length of the solenoid times A. And the third point is that the general definition is going to be EMF equals minus L times dI dt. And if you're not in a calculus-based physics class, then this just amounts to delta I over delta T. Okay, so there are your concepts.